This is section 13.2, vectors in 3 dimensions. Up above my head here, we've got all the different data points, not data points, data types that we're going to work with in this class. The one called vectors is labeled R3. It's got like this fancy R and then 3. The fancy R is for real numbers, and R3 represents 3 real numbers, like all of the points given by 3 real numbers. So R3 is our summary, not our summary. R3 is our abbreviation for points in space. Instead of everything having an x coordinate and a y coordinate, in this section, and for most of the class, everything will have an x coordinate, a y coordinate, and a z coordinate. So that's the goal for this section, is to understand the components and vocabulary of vectors when we move into 3 dimensions. And then we'll just try to get some refreshers of how geometry works and apply it to 3 dimensions. And finally, we'll graph vectors in space. Graphing things in 3 dimensions is a little tricky because I don't have 3-dimensional paper. But you should practice doing the drawings. And then also I'll make sure to show you my favorite 3D grapher online so that we can so you have a tool to use to graph things if you're not sure what they're supposed to look like. Okay, first thing is let's get the basics of the coordinate system when we're in 3 dimensions. The main thing to do is to make the x-axis come out at you, and then the y-axis can go more or less horizontal. This tries to give you the perspective of the xy plane being a sheet of paper that's kind of flat, and then the z-axis will be the vertical axis, and it will come out this the wiggly axis. The z-axis will go out vertically like this. So these are the positive axes. Because we're drawing on 2-dimensional paper and we're trying to draw 3 dimensions, it's always going to be a little bit sketchy, but that's okay. So those are the axes. Then there's planes that are the coordinate planes. So if you set z equals 0, z equals 0 is all the points in the xy plane, like on the flat plane of the ground here. So z equals 0 is called the xy plane. If you instead ignore the x's, you set x equal to 0. X equals 0 is everything that's, it's in this plane that's flat on the paper. Like back here, with the x-axis sticking out of it. Everything in there, because all the y's and the z's might not be 0, are called the yz plane. And then the other one we can do is we could set y equals 0. Those would be things on this plane. Where it's kind of slice coming out at us. Those are the points where y equals 0, and that's the xz plane. I only know one trick for drawing things in 3 dimensions, and it's that parallel lines stay parallel when you look at them from a different perspective. So to try to draw things that were parallel to the x-axis, I just drew lines on the page that were parallel to my x-axis, and they come out kind of looking like they're headed in the right direction, as long as you talk about it while you draw it. Okay, you had quadrants in 2 dimensions. You had the xy plane, and the the first quadrant was the one where the x and y coordinates were all positive. Instead now, in 3 dimensions, there's 8 octants. Because x, y, and z could all be positive or negative. So there's 2 times 2 times 2 possibilities. So there's 8 coordinate octants instead of quadrants. We don't try to number all of them. We numbered all the quadrants in the xy plane, the first, second, third, and fourth quadrant. We don't try to number them all, but we do declare that the one where everything is positive is the first octant. So if all the coordinates are positive, we call it the first octant, but no one will ever ask you to draw something in the second octant because nobody has decided which one is second. Or if they have, I don't know, they never told me. But the first octant is a good shortcut for us to have. Okay, let's practice graphing a little bit. What I recommend doing if you're graphing a point is to first look at what happens in the xy plane and then go up from there. So here's my x and y axes, and then I'll have a z axis in this direction. When you're drawing tick marks on the axes, make them parallel to one of the other axes. So on the x-axis, I'm going x equals 3. So here I'll go up to 3. And then on the y-axis, the critical little detail to do is to make these tick marks parallel to the x-axis. It just gives you a little bit of perspective to show that in the xy plane, we're kind of like on a flat plane that's supposed to be, like horizontal, and then z we're thinking of as the vertical axis. So you go over to 3, 2, and to do that, you follow like parallel to the axes. So here's 3, 2, 0. And then to go up by 1, you go up by the same amount that you would go up on the axis. And then label it. This is 3, 2, 1. These dotted lines help us see like what you're trying to do here. You'll never be able to just put a point on the page and declare that that's 3, 2, 1. That just doesn't really work. But I recommend getting the x and the y to be set up first and then go from there. Technically, you could draw like a whole box here. So you could like go up by 1 on the x-axis and y-axis too, and like draw this entire box to show that, well, if you could go up 1 and then over 2 and then out 3 if you wanted to. Any order would work. But as long as you do at least one of these combinations to show like what path we're trying to take to get to the point, then it makes your picture more believable. Okay, the distance formula. So we have a distance formula in 2 dimensions, which is you just square the 2 components, add them up, and take the square root. It turns out that the distance formula in 3 dimensions follows the same pattern. Why? Well, let's see. So I'm going to draw a box. Let's say it's remember, I'm still following the only trick I know, which is to make things parallel to other things if they're supposed to be parallel. So let's say you're trying to get from here, from point A to point B. And you're going to go some distance in the x direction, some distance in the y direction, and some distance in the z direction. What I want is the distance across the middle of this box. Well, how will I do that? I'll do it with the Pythagorean theorem because that's all I have. So I'll try to find this distance on the xy box, and then I'll go up by z. So this triangle will be the right triangle that I'll use to figure out the total distance d. Okay, well, what is the total distance d? Well, I need to take the square root of this like weird diagonal squared plus z squared. Because I'm just using the regular old Pythagorean theorem here. The question is, what is this weird diagonal? And the answer is that this weird diagonal is part of this triangle. So this weird diagonal distance comes from the Pythagorean theorem on this triangle, which is flat on the ground. So it's square root of x squared plus y squared. And what you notice when you do this, when you like just write out what happens with the 2 triangles, is that when you like square the square root, and so you end up with something that's symmetrical in all 3 coordinates. So it doesn't actually matter which coordinate you think of as like the x or y or z coordinate. You take all the components, whether there's 2 or 3, square them all, add them up, and take the square root of the result. So that will be our distance formula in 3 dimensions. This is technically a proof of the distance formula using the Pythagorean theorem, but I didn't write it like that. So between 2 points, you take the difference of the x's, square it, the difference of the y's, square it, and the difference of the z's, square it, add them all up, and take the square root. That's the distance. This formula will end up being really important because we're going to be talking about vectors pretty soon, and the magnitude of a vector came from the distance formula. So the magnitude of a 3-dimensional vector is going to look like this. let's do some geometry first before we deal with some vector stuff. So let's think back to what is a sphere. A sphere is all the points, and I'll give them a name, all the points x, y, and z that are a fixed distance, r. So you like pick a radius, and you pick a center point. I need a name for the center point. I'll generally use x0, y0, and z0. Remember, these subscripts are adjectives. So this is the 0th x. That means it's like the base x, and the base y, and the base z. Where up here, the subscripts were adjectives. You were supposed to think of x1 as like the first x, and x2 as the second x, because that's how you turn numbers into adjectives. So this is like first x, first y, first z, second x, second y, second z. And down here, this is the base x, or starting x, starting y, starting z. So this is what we mean by a sphere. The question is like, okay, if that's what a sphere means, then like, can we write it as an equation? And the answer is sure. You just write down the distance formula. The distance, r, you can drop in for the distance formula, and all the other points you can just drop in where they go. So this is the equation, this is an equation for a sphere of radius r centered at x0, y0, z0. Usually we don't write it this way because it's ugly. Usually we square both sides so that we get a nice looking formula. But the equation, the standard equation for a circle, the standard equation for a sphere, they're all the same thing as the distance formula. And the distance formula is all the same thing as just the Pythagorean theorem. So it's all kind of like one common fact. Okay, we can write it a different way, I guess. If you already wrote down the other one, you don't have to do this. But we'll say that with radius r and center ABC, just to make it look even cleaner, they're not all x. It's x minus a squared plus y minus b squared plus z minus c squared, all equals r squared. And this is our nice formula for the equation of a sphere. Okay, what other geometry can we do? Well, there's going to be some questions that talk about the diameter of a sphere, and so we're going to need to be able to find, like, the diameter of a sphere would be 2 points that were, does this show up? Yeah, 2 points that are, I would give you like 2 points on opposite sides of a sphere, and then ask you to find the equation of it. To start, you'll have to find the midpoint between the 2 points. Luckily, it's just as easy as it is in 2 dimensions. The midpoint is the average, and to find the average of 2 numbers, you add them up and divide by 2. So you add up the x's and divide by 2. This is the average x, and you find the average y, and you find the average z, and that's the midpoint. So when a question asks you, find a sphere, here's some points that are on opposite sides of the sphere. Okay, well, the center point is going to be halfway in between. Take the average of the x's, the average of the y's, the average of the z's. Using the formula is a little bit silly here. Like, what's halfway between -1 and 1? It's 0. What's halfway between 7 and 3? That's 5. Halfway between 4 and 6 is 5. But the formula also gives it to you if you want that. So here's the center point. And then the radius is the distance from the center to the edge. Or you could find the distance between the 2 outer points and divide by 2. Either one would work. I'll just find the distance between the center So here I'm dropping in the center point between the center and one of the endpoints. Let's use this one. this will tell us what r is. So the radius of this sphere is the square root of 1 plus 4 plus 1. So it's square root of 6. To put it all together, the equation, there's lots of equations for any shape, but the best, easiest equation for a sphere is you just drop the radius, this number square root of 6, in here, and you drop the center point into ABC. So our easiest equation for this sphere will be x minus 0 squared plus y minus 5 squared plus z minus 5 squared is r squared. So this is r, this is r squared. So here's our equation of our sphere. I kind of want to show you the easiest online graphing tool, and so that we can just practice graphing something, and so that you have the ability to like play with surfaces and other graphs as we run into them. The easiest one that I know of is GeoGebra, and the 3D graphing calculator is geogebra.org/3D. So let me switch over to that to see what it looks like. If we type this sphere in, I use the caret like shift 6 to get an exponent. I get x squared plus y minus 5 squared plus, ooh, we're getting weird surfaces here. We'll deal with specific shapes of surfaces later. And all that adds up to 6. What you get is a sphere, and you can like kind of set it spinning so that you can get an idea for what it looks like. There's just out there at 0.55, there's a sphere with radius square root of 6, which is like a little more than 2. So there's just a ball out there. If we changed this number, we could make it a lot bigger. And you can just see what happens as you play with the terms. You might remember from Calc 2 or maybe pre-calculus that if you change one of these into a minus, you can get like weird hyperbola shapes. We'll play with all that. We'll play with all the different strange shapes later. I don't remember what happens if 2 are minus. Oh, that's sweet. So you can just play. I don't know. Let's make this x to the 5th. No luck. Oh, I guess we can't just play however we want. The shape disappears. Where's my shape? Huh. Well, it's not a very good advertisement. But all the normal shapes that we run into, it should be able to graph them. I'm like really disappointed. I must be missing something. Okay, let's get back to 13.2. So now we'll deal with vectors in space. The main thing about vectors in space is that they work the exact same way as vectors in the plane worked. We can write them in component form. We can write them with i's and j's, except we'll need I, j, and k. We often will not try to write them in terms of their magnitude and direction because there's like a lot of, I don't know, the angle situation is a little bit tricky. So we won't deal with the angle situation for a little while. So our notation that we'll generally use is you will write a vector in component form by writing 3 components: the x component, the y component, and the z component. So this is component form. The other way you could write it is you could say, okay, well, you could write some multiple of I, some multiple of j, and some multiple of and some multiple of k. And the understanding that we have is that I is the vector that goes in the x direction, j is the vector that goes in the y direction, and k is the vector that goes in the z direction. You should imagine the power of this notation is that just in case you ever need more than 3 dimensions, vectors are ready for you. Like nothing will stop you from just making the vector be in 5 dimensions. you're probably thinking of all the dimensions as being space, but they don't have to be. So like even though the space around you is 3 dimensions, you might add a 4th dimension of time, and then you might add a 5th dimension that's like the temperature, and the 6th dimension could be the population density, and then you can play with all the different I don't know, levels of everything. Yeah, vectors are powerful. We'll mainly deal with 2-dimensional and 3-dimensional vectors, which is why vectors above my head is labeled R3. But you can go higher if you want to. Anyway, our distance formula tells us that to find the magnitude of a vector, which you can write with an absolute value bar, or if there's other absolute values around and you want to be careful, you can write it with double bars, is, well, same deal as with 2 dimensions. You square all the components, add them together, and take the square root. And then if you want to make a vector into a unit vector, that's called normalizing it. And you can make a unit vector by dividing a vector by its magnitude. This had nothing, like, we had this formula for 2-dimensional vectors, but there was nothing about it that was special for 2 dimensions. And that's the power of vectors. It's going to happen a lot in this class where I realize that we're about to talk about linear algebra, and then I go, this isn't a linear algebra class. And that's going to happen more and more if you're taking more and more math, that like linear algebra is gradually going to take over because it's super powerful. This is the power of linear algebra, the math of vectors and matrices, that we don't care how many dimensions there are. This formula works no matter how many dimensions there are. Similarly, the way addition, subtraction, negation, and scaling worked, it still works all the same in 3 dimensions. If you multiply a vector by 2, you just make it twice as large in every direction. Okay, on to the last page of this section. Let's try to find a unit vector that starts at 2, 1, 5 and ends at... What? A unit vector can't do that. Oh, let's have a unit vector point in that direction. So we'll stand at point P and look at point Q and just look for a unit vector that goes that way. So my plan is to first find a vector, PQ, then normalize it. And normalizing it means making it so that it has length 1. So let's get it. PQ, the vector, is a vector where you do the difference of all the components, and you always do end minus start. So we've got -3 minus 2, 0 minus 1, and 4 minus 5. So this vector is the vector -5, -1, -1. Now this vector is much longer than length 1. It goes 5 in the x direction. Like in total, it's much longer than 1. So to normalize it, we find its magnitude. That's square all its components, add them together, and take the square root. Square root of 27. 27 has some 3's in it. So we'll split this up as 9 times 3, and square root of 9 is 3. If your final answer is the square root of 27, that's okay, but it's kind of like calling it's kind of like calling a pizza place and asking them for 4 halves pizzas. Like, hi, I'd like 4 halves pizzas. And they go, what? And you say 4 halves. And they say, 2? And you go, yeah, 4 halves. And they go, okay. And if you circle square root of 27, I have the same reaction as the pizza guy in that story. It's like, okay, I guess, but like, do you not know what that means? So just try to simplify things. If you don't remember how to do this, you'll be really fast at learning it. Just like I talked about last section, when you find something that you're not an expert in, just look back and figure out how to become an expert in it. And I can help you. Let's build our unit vector. Our unit vector is our old vector divided by its own magnitude. It's scaled down. And when we scale it down, we'll get -5 over 3 root 3, -1 over 3 root 3, and -1 over 3 root 3. We've scaled down this vector so that it's a unit vector. All vectors have a magnitude and a direction. We think of this kind of vector, we think of a unit vector as kind of having like no magnitude information. which is weird because its magnitude is 1. Like, it has a magnitude. But we think of it as we've removed the magnitude from the vector, and now it's just pointing in a direction. So a unit vector is supposed to represent mostly just the direction it's pointing. Okay, let's describe the position of this vector just to get in example 4, just to get familiar with what 2j plus 4k means. Well, it points like in the y and z positive direction. But it doesn't go at all in the x direction. So the easiest way to say that is that the vector stays in the yz plane because it has no x component. Getting familiar with the various coordinate planes is very helpful. In 2 dimensions, it was like not that hard. If y equals 0, you're on the x-axis. If x equals 0, you're on the y-axis. And in 3 dimensions, it just feels a little more tricky. It's not actually more tricky. If x equals 0, then you're on, well, the others. That's the yz plane. If y equals 0, you're on the xz plane. So it's like whichever thing is 0, you're in the plane of the other two. So let's just summarize that. In the xy plane, that's z equals 0. In the xz plane, y equals 0. And in the yz plane, x equals 0. So these vectors look like a, b, 0. These look like a, 0, c. And these look like 0, b, c. So that's nice. I mean, if you set a variable equal to 0, you land on one of the coordinate planes. How do you actually land on the axes? Well, to land on the axes, you do the opposite, where to be on the y-axis, you need everything except y to be 0. So to be on the y-axis, you need to be like 0, y, 0. To be on the x-axis, you can be any value of x, but the others have to be 0. And to be on the z-axis, you can only have a z component. Nice. If we had a computer lab, we would like type some crazy stuff into a program called Maple, and you would get to explore what the vectors look like. As you can see from the code here, it's not particularly simple to do that, and we don't have access to a computer lab right now anyway, so I guess we'll skip this for now. Yeah, so do some homework problems to just practice getting used to 3 dimensions, and try to ask yourself as you're doing things whether this is different or the same as it would be if you were doing it in 2 dimensions, like for all the problems. That's 13.2.